Okay, so we're going to start with section 33, right? And number 6, is that what you said?
Number 5.
5, sorry. 5. Okay, it says, here we go. So we've got 16 to the x minus 3 equals 8 to the y, and we're trying to solve for y. Now when it says in terms of x, don't let that bother you. Basically, you're just trying to get y by itself, okay? And you're going to have x as part of your answer. So when they say in terms of something, that means, like if they say in terms of x, that means that x is going to be part of your answer. So y is equal to something something x, okay? So that's what they mean when they say in terms of x. So basically, what you have to do is basically just solve for y right there. Now, it's very difficult to do this just like regular algebraically, all right? In fact, I don't even know how you'd begin doing it just by some kind of algebra thing. So what we're going to do is we're going to use logarithms, right? And then that we have a lot more rules for logarithms than we do for exponents, okay? So that's what we're going to do. So we can do what? We can take the log of both sides, can't we?
Mm-hmm.
So I'm going to take the log of this side, and we'll just say it's log base 10, okay? So we'll just go regular log. And this is 8 to the y. All right, so now that actually gives us some options here, doesn't it? So if I have a log here, what can I do with that?
You can make it so that you add exponents.
Well, now nothing's being multiplied together. It's called the power rule. Do you remember if you have the log, I don't know, base b of, I don't know, x to the third, what can we do with that 3 right there?
Can you move it in front?
Exactly, you got it. Okay, move it in front. Make sense?
Mm-hmm.
And that way, now we don't have exponents, right? So it's kind of hard to get x by itself if it's in the exponent. So what we want to do is we want to make it so it's not in the exponent. And by putting logs here, that allows us to put it out front. Does that make sense?
Mm-hmm.
Okay, so what we're going to do is go put that x minus 3, take this whole entire exponent, we're going to take that, we're going to toss it out front. All right, so let's see what we get. Now, that's being multiplied by the log of 16, so I'm going to go put that in parentheses because it's being multiplied by the log of 16. Okay? And we're going to do the same exact thing here, aren't we? We're going to take that y, and we're going to put it out front. So that's going to be y log of 8. Now again, what are we trying to solve for here?
Y.
Yeah, so let's make sure we don't lose track of what we're actually solving, because they're two variables, aren't there?
Mm-hmm.
So we're solving for y in terms of x, so x is going to be part of our answer. So I want to get rid of this. So what are you going to do? The log of 8, remember this is base 10, this is just a number that you can put into a calculator. All right, so think of it just as any ordinary number. Like what if this was 3y equals all that stuff? How would you get rid of the 3?
Would we subtract log of 8?
No. Watch. If this was like 3y is equal to, I don't know, 12, make it real simple. How would you get y by itself here? Divide by 3, right, because what's that 3 doing to that y? Okay, what is this log of 8? Remember, this log of 8 is just it's a number, right? I can chuck it into a calculator and it's just some decimal number. What is this number doing to y? It's multiplying, so how do I get rid of it? I divide, okay? That's what you have to think of. Don't think of this as some crazy thing right here. Just think of it as a number. It's a decimal number, but just as a regular number. If a number is being multiplied, how do I get rid of it? I divide. So I'm going to divide by the log of 8. So I'm not sure exactly how they write the answer here. Watch. They may have distributed this through first. I'm not really sure. But we'll write it like this. And then I'll have to take a peek at the answer just to see what form they put it in. Okay, they could put it in several different forms. So we've got that, we've got that. They probably do simplify this. Let me think for a second. I'll tell you what, let me take a quick peek at the answer first to see which direction they go, and then I'll show you what they did.
They don't even know who you are.
That's right. Okay, let's take this. I think I'm going to see, remember the log of 16 is just a number as well, isn't it? It's being multiplied by this. So let's distribute this out and see what we get. So this would be x log of 16 minus 3 log of 16, correct? And that whole thing is being divided by log of 8. All right? And that's all equal to y. So it's a matter of just simplifying this. And they do get rid of the logarithms here. All right, after looking at this, I don't think that we need to do all this right here. I think we can just stay right here and just put this into the calculator. All right, so bring the calculator up, and we've already done it, but we'll do it again. So what I'm going to do, see how this is x minus 3 times this? So I'm going to go log of 16 divided by log of 8 and see what that comes out into the calculator. All right, so we'll do this, log of 16 divided by log of 8, and see what we get. That's 1.333, and 3 repeating is the same as a third. So that decimal right there, oops, that decimal right there is 1 1/3 times x minus 3. I think that's what they want you to do. So it's, watch, x minus 3 times, and would this thing come out to be? 1, not 1/3, but 1 1/3. But they don't usually like to write it like this. We would write it as a improper fraction normally. So how would I write that as improper? 3 times 3 is, or 3 times 1 is 3, plus 1 is 4/3, right? So it's 4/3. We'll put that out front, just looks a little bit better, x minus 3. And that's what y is equal to. So that's what y is in terms of x. It just means that x is in the answer, okay? Now, they give you a second version of this answer as well. What they did is they distributed the 4/3 through this. So you could have written it like this as well. You could have said 4/3 x minus, what's 4/3 times 3? 4/3 times 3. It's just 4, isn't it? So you could have written it like this as well. So either one of these would be acceptable. And they actually give you both of those versions in the answer key. Do you guys have the answer key to the regular problems? Okay. All right, so that's how you got that.
The videos and just skip to the end of the video and see if I got it right. But if I got it wrong, I go back to the beginning of the video and watch.
So you have a video that shows you how to do all the problems from the homework? Do you really? Yeah, we talked about this before, didn't we? I always forget. Yeah, I don't have one of those. I'd like to have one of those.
He doesn't explain it well enough. A lot of times they just assume that you know what you're doing.
Right.
And like, here's what you did wrong.
Right.
Kind of thing.
Okay. So they don't explain it as thoroughly as they do, like on the when they teach the stuff. Okay. All right. Let's do another one. All right. So now we're going to do number 12, and we have to solve for x. All right. Just say solve. So let's see. What are we going to do first? I see what we're going to do right off the bat. What do you think would be the easiest thing to do first? What do you think?
Subtract the 15.
Yeah, I would subtract a 15 from both sides first. All right, so let's just do one step at a time. So if I subtract a 15 from this, it's negative 16. Okay. One more step that's fairly simple to do. Fairly straightforward. What do you think?
Divide by negative 2.
Yeah, divide by negative 2. All right, so divide by negative 2. That'll cancel that out. Right? And so we've got x to the 3/5 equals negative 16 over negative 2, just positive 8, right? Okay. Now here's, I think this is new, isn't it? I think this is,
We may have had
I think.
in a past lesson.
Did you? You could do this a couple ways. You probably could do this with logarithms, but I'll show you another way. And I think on one of the lessons, he kind of talked about this a little bit. Remember, we want to get x by itself, don't we? So I want x to the first. Okay, so there's a rule that I can do with exponents. For instance, let's just back up a little bit. If I said x squared to the, I don't know, 5th, what's the rule here? How do I figure that out?
Add exponents.
What do I do?
Add exponents. Or multiply.
You tell me. Which one? What about this?
Oh, so it worked.
One's one way, one's the other way. Which one's which?
Multiply is the first one, and then the second one is add.
Which one first one? Is this first or second?
The bottom one's
Okay, the first one that I wrote down. Okay, right. So the first one up here, you add them together. So it would be what? X to the 7th. And this one down here, what do I do? Multiply together. Okay, so the rule says if I have an exponent taken to another power, I multiply the exponents. Agreed?
So could you take it to the 5/3?
Exactly, right. And that's what I want to do because I want this to be x to the first. How can I make a 3/5 and multiply it by something to make it a 1? Well, multiply by its reciprocal. Would you agree? Yeah, and if I do that to this side, I can do it to the other side. And I take this to the 5/3. Okay? Does that make sense?
Mhm.
So that's how I can get rid of a fractional exponent like this, multiplying it by the reciprocal, and that'll be a 1. Anytime I take a number, any number, okay, and multiply it by its reciprocal, I'll get a 1 out of it. So that cancels out basically, doesn't it? But now you get a weird looking answer. You get 8 to the 5/3, but we don't want to leave it like that. We can actually break this up. And this still goes back to this rule right here, but it's kind of going the other way. Like if I said, can you rewrite this with 2 exponents? Yeah. You could write it 2 ways. You could write it x to the 5th squared, couldn't you?
Mm-hmm.
Isn't that the same as x to the 10th? Or you could write it like this, x squared to the 5th. Agreed? So we could do the same thing here. So watch. We could write it x to the 5th, right? Because what is 5/3? 5/3 is 5 times 1/3. Agreed? All right. So really, there's 2 things being multiplied to give you 5/3. Just like there was right here. There's 2 things that multiply to give you 10, right? 2 times 5. So I could take it x to the 5th to the what? To the 1/3. Now look, can you do x to the 5th in your head? It's x times x times x times x times x.
Mm-hmm.
Or not x, 8. Sorry. Why am I saying x? 8 to the 5th. So 8 times 8 times 8 times 8 times 8. Can you do that in your head?
Not really.
I definitely could not. Okay, it'd be some big, huge, crazy number. You could do it in a calculator. You definitely couldn't do that in your head, could you? Then you would have to take that big, humongous number, right? Because 8 and then do what to it? Take it to the 1/3. What's the same thing as taking it to the 1/3 power? I think we discussed this last time, and he might have talked about it in one of these lessons.
Flipping it up, making it negative.
No.
Flipping it upside
We
down.
started making a little list. I think we did this last week. The square root of x is the same as x to the 1/2. Do you remember seeing this?
So it would be the square root.
And then the cube root of x is the same as x to the what?
1/3.
1/3. So if it takes something to the 1/3 power, I'm taking the cube root of it. Is there any way that you, in your head, you could take the cube root of that big, humongous number that I can't even do in my head? No, I don't think so. So I'm not going to do it this way, all right? Even though technically that would work. I just can't do it in my head. They've rigged this thing, all right? They have. They've rigged it so you can do it in your head. Watch. Well, at least most of it in your head. Yeah, you could do it all in your head. Watch. Instead of x to the 5th to the 1/3, what's another way we could do this? Just like there was 2 ways to get x to the 10th, we could go what? 8 to the 1/3 to the 5th. Isn't that the same as 8 to the 5/3?
So it would be square root.
It's not square root. It's cubed root, right? So what number times itself 3 times is going to give you 8? 2. Right? 2 times 2 times 2. So the cube root of 8 is 2. So we could do that in our head, couldn't we? And then you take 2 to the 5th. And you can actually do 2 to the 5th. After you get used to these and you do these a lot, you kind of memorize what 2 to the 5th is. But let's do it. 2 to the 5th. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. One more 2 is 30. Nope, 2. So it's 32. And that's your answer right there. So 8 to the 5/3 is the same as 32. Let's see if it actually works. Watch, you could do it like this. You could go 8, right? That's your exponent, right? To a certain power, that little arrow thing right there. 8 to the 5/3. Let's put 5/3 in parentheses. 5 divided by 3. And let's see what we get. Hopefully we'll get 32. Yep, look at that. Now that would have been a little, a little quicker. But I want to show you, though, how you could do it in your head and why they picked over 3 and an 8. They did it on purpose, okay, so that you could do it in your head and not have to jump to a calculator. You follow me on that? Now, you could have done it the other way. You could have got, remember I said, let's go 8 to the 5th and then to the 1/3. Let's see what that looks like. 8 to the 5th. Let's just see what that number is. Remember we said it's a big, crazy number? Look at that. I would have never been able to come up with that in my head. And then we got to take that number and take the cube root of it, don't we? All right, and let's see. I think you can take the cube root by going to math, can't you? Yep, there's a cube root button right there, 4. So there's the cube root of that number, and I can put answer right there. See what it's doing? It's taking the cube root of this, and guess what we should get?
32.
Let's hope. Yep, sure enough. Okay, so it works, doesn't it? I kind of like my way of doing it, okay? I don't mind calculators, but if I don't have to use it, I'd prefer not to use it. And I can do that pretty simply without using it. All right, is that good enough? Now, you could have gone logarithms on this as well if you wanted to. Right, you could have put a log in front here, take the exponent, put it out, right, in front and all that. You could have done that if you wanted to, and it would still work.
I'm still not a big logarithm fan.
You're not a big logarithm fan? Oh, really? Because I tell you what, logarithms really, really help you out sometimes. I mean, like right here. That would have been impossible, wouldn't it? To do this problem right here. I mean, it looks fairly simple, right? It doesn't look super, super complicated. In fact, the one we just finished doing looked more complicated than this one, to tell you the truth. I don't know. I thought it did. But you really wouldn't be able to do this if you didn't have logarithms. Okay, so logarithms are your friend. They're trying to make things easier for you, okay? All right, let's do another one. We're being silly. All right, what else we got? All right, so now we're going to do problem set 34, and we're going to do number 10. All right. Yeah, another one of your friends, a logarithm. Once you learn the rules for logarithms, it's really not that hard. I mean, they scared me too. I remember when I first did this. I was in college first time I saw logarithms. Can you believe that? I wasn't that accelerated in high school in math. I just liked it for some reason. I don't know why. I wasn't even like super good at it, but I just liked it more than anything else. And so I became a math major in college. Probably, you know, if I was to give words of wisdom to somebody, I would say you got to be pretty decent at it to be able to be a math major in college, because I really struggled. But if you're decent at it, I think you can do it. I was less than decent. I was average to maybe a slightly below average in my math abilities. But I enjoyed doing it, you know. So I stuck it out.
I've enjoyed it till this year.
Until this year?
Really hard.
Yeah, this is definitely.
I've gotten an A in every math I've ever taken so far, but now it's kind of gone.
Yeah, this one definitely is. It jumps you up quite a bit, pretty quick too. All right, you ready to do this?
Advanced math. I was going to do an advanced math this year, but
yeah,
that was even harder than this is.
Yeah. But after a while, after you start doing these things, then you look back on it, man, I thought that was really super hard, but yeah, it wasn't as bad as I thought it was. I don't know, do you feel that way at all sometimes?
On
No?
some of the problems at the beginning of the book, but...
Okay. All right, here we go. What's the rule here? Look, I got a log. They all have the same base, okay?
Can I take all the logs out?
No. You got it. There's a rule with this logarithm and this logarithm. It's not a multiply. No, this minus means you do what?
Divide.
And where do we get that from? Like if I had something like this, if I had x to the 7th over x to the 3rd, what's the rule for exponents here? I keep the base the same, and what do I do with the exponents?
Subtract.
I subtract. Do you see the relationship between subtraction and division?
Mm-hmm.
Okay. Remember, logarithms are exponents, aren't they? It's just another weird way to write an exponent. Okay. So subtraction and division definitely have a relationship to each other. So as soon as I see this subtraction, I see logarithms, I'm thinking what?
I'm going to divide.
I'm going to think I'm going to divide. That's right. So what I can do here is I can just put 1 log, right? Keep the base there, 1 log, and then do what to these things? Divide. Okay, you always take the first one, divide it by the second one. So it's going to be x divided by 3. That's one of our rules, okay? If you need to, go back to that lesson where they taught it. I'm not sure what lesson it was, but go back and review those again, okay? And make sure you know those logs, because once you know these rules for logarithms, it makes things a lot easier. Now, wouldn't you agree that that looks a lot better than that whole mess right there?
Yes.
Yeah. Now, I can't really do much with this, so I'm just going to keep it log base 2 of 7. Now, this is where it really gets nice. And this is where it's really nice to have logarithms, because we're actually going to get rid of the logarithms, all right? Because log of this equals log of that, so this equals that. Remember me saying that? Okay. So the log of this thing equals the log of that thing, so this thing equals that thing. So basically, the logs just cancel. Okay, so I'm left with just x over 3 equals 7. Now it's a piece of cake. So multiply both sides by 3, so x is 21. Always look to see if it works. Does 21 work? Can I put it in for this?
Yes.
Yeah, exactly. And the reason why it wouldn't work is if this argument, right, it's whatever you're taking the log of is called the argument. If that came out negative, then it wouldn't work. But you put a positive 21 in for x, that's positive already, so it's fine. And so we can circle it, and that's our answer. So x is 21. We good?
Yes.
All right.
And then these are...
All right, here's a crazy looking problem. says y equals f of x. It says y varies inversely with the square of x. That phrase right there, y varies inversely with the square of x. There's a way to write that. Do you remember he talked about the inverse square rule or inverse square law? That's a very popular law. I taught physics for a bunch of years, and we use that in physics. And he went through a little bit of explanation. I won't go through all that. But that is something that you'll see quite a bit if you do take a physics class. What science are you guys taking now? Like chemistry? Okay, what are you? You're still in biology, right? So when you take physics, you'll learn about this inverse square law. And it's actually a pretty interesting law. It deals with a lot of things. And he explained it a little bit in the video. But how do we write this? How do I write inverse relationship and a direct relationship? Because that's what the two things he was talking about. Let's do direct first, okay? This doesn't have anything to do with this problem, but you might have another one where it says it varies directly with. So when it says varies directly with, this is how you would write it. You would write y equals, I think it's just ax, okay? That's a direct relationship. That means when x goes up, what's going to happen to y? That's going to go up, all right? It varies directly, right? So watch this. If y equals 3, let's make it even easier, 2 times x. Watch. If x is 1, what's y?
X is 1, y is 2.
Yeah, okay. So watch. As x goes up, watch what happens. As x is 2, what's y?
It's 4.
It's 4. As x is 3, what's y?
6.
It's 6. You follow me on this? What if it says inversely? We're not even going to do the square just yet, okay? Let's just do a regular inverse relationship. So it would be this. It would be y equals a over x. You follow me? So let's just make a equal to 1. So what if I said this? Y equals 1 over x. Let's look at the relationship here. Let's put a number in here. Let's put a 1 in for x, okay? So if x is 1, what's y?
1.
1 over 1 is 1, right? What if x was 2?
It's going to be 1/2.
It's going to be 1/2. Do you see what happens? As x gets bigger, what happens to the y? It gets smaller. Do you follow me on that? So that's an inverse relationship, all right? Because they're inverses of each other. If one gets bigger, the other gets smaller. They're inverses. Make sense? Direct relationship or a direct variation means as one gets bigger, the other one gets bigger. Does that help a little bit? Understand what those words mean at least? Okay. But this says y varies inversely with the square of x. So how am I going to write that? I use the a because remember I said y equals 2x. We don't know how much it varies, right? It could be twice as much or 3 times as much as 4 times as much. That's what the a represents. How much is it going to vary, okay? Like on the inverse one I did earlier, I said a was 1, right? I could have put a 2 in there, but or a 3 or 4, whatever. But I'm just going to put a for that number. So if it varies inversely, that means I'm going to have a fraction with the square of x. So it's not just going to be a over x, it's going to be what?
Ax squared.
A over
X
x squared, exactly. All right? So that is the key right there, is to set that thing up. You got it? So what we're going to do, look what they tell you. They say when x is 4 and y is 1/2. So what we're going to do is we are going to solve for a. All right? So now he talked about this other way to do it a little easier without doing the math. I don't know if you remember that explanation. Do you remember that one where he said, you could do it this way and solve for a, but here's a little bit of an easier way. And his explanation, tell you what, didn't make it sound easier. I mean, I understood exactly what he was saying, and I get it. But I was sitting there thinking while he's talking, I'm thinking, you know what? I think they're going to be really confused on this. I'm just going to show them the way just to do it mathematically, okay? And I'll try not to make it more confusing than it already is. So what we're going to do is this. We're actually going to find what a is, right? Because look, they tell me x and they tell me y. So where am I going to put those? In for here, and then I'm going to get a by itself, okay? So watch what I'm going to do. Let's go back to blue. So what is the y? Y is 1/2 equals a. I don't know what a is. That's what I'm trying to solve for. Over x squared. Well, x is 4, so it's going to be, we just do that in our head, we'll just go 16, correct? All right, follow me? Now, let's solve for a. How do I get rid of the 16? Multiply by 16. So I come over here and I multiply that by 16. It's going to be 8, right? Because half of 16 is 8. So a is equal to 8. Got it? Now, that's not my answer, though. They want us to solve for y when x is equal to 1. Well, I'm still going to use this formula, but what's the only problem? I didn't know a before, did I? So, but now I do know a. So what I'm going to do is I'm going to put the a, or the 8, in for the a, and then solve for y, and I'll put a 1 in for the x. Does that make sense? So let's solve for y. Let's do this in a different color since we're solving for something different. So I'm going to go solve for y equals a over x squared. Well, I just found a, which is an 8, over x squared. Well, x is 1, isn't it? So let's put a 1 and square it. That's pretty easy. So what's y equal to then? It's just 8. And that's your answer. It's not always going to be, y is not always going to be the same thing as that a is, okay? It happens to be in this problem. It's not always going to be. All right, but that's how you would do that. So that's not too bad, is it? But the thing is, you have to know that relationship. You have to know that y equals a over x squared. If you didn't know that, you'd be sunk, okay? Make sense? Does that make it a little easier? All right. You want to do 17? Okay, this is a direct relationship. So it says y varies directly. So I'm not even going to write out the words. Directly with the cube of x. So how are we going to write that? Y equals what?
Ax squared.
Good. Not squared. Cubed.
Oh.
Right? Big difference. All right. When, I'll just put this. When x equals 1 and y equals 6. All right? And it says find y when x equals 3. All right, so here's our relationship right there. So if I want to solve for y when x is 3, what's my only problem? I got to find a, don't I? And where do I find a? I find a from this information right here. Okay, so we're going to go, yeah, you're getting the hang of it, aren't you? So you got 6 equals a times x cubed, which is 1 cubed. That's easy. That's a 1, so a is 6. And now we're going to use that a for right here, right? So now we know what a is, and now we just solve for y. So y equals 6 times, now this time the x is what? 3 cubed, and I don't know, whatever that is. 27 times 6, 20.
Which is 162.
Yep, 162. And that's it.
Now I understand.
So that made, yeah, so that made something that was kind of difficult, made it pretty easy, didn't they? And I think he should have probably done a little bit more of this.
I did not understand how to do those problems
Right.
whatsoever.
Now the key is, I keep saying that, is this thing right here. Know what it means to vary directly and know what it means to vary inversely. Okay? Or some books and authors will say indirectly. All right, inversely and directly, same thing. Got it? Okay. I don't know if you have a question on this one or not, but that's ugly.
Oh, it's the stepping.
Yeah, it's that greatest integer function. Now he used this int. I had never seen this int used before. And then he said, well, some books or some authors use this other symbol. And then he gave some crazy symbol that I have never seen before, but I used something close. Watch this. And x equals 1.25. And then it says find y. Now when it says find y, it's actually f of x is the same as y. Would you agree with that?
Yes.
All right, so basically they're saying find that. Basically, they're just saying find this int means the greatest integer function. Now here's another way that I have seen it written, just in case, you know, if you're in college or something, you're taking a math class and they say greatest integer function, and you're like, I never saw that before. This is how I've always seen it. They just put it in a bracket. Now his bracket, do you remember the bracket that he used? He used some crazy bracket, like it went straight down like this. Do you remember that one? Or he did it on top or the bottom. I forget exactly how he wrote it out. But I thought that was a little odd. I've always seen it like this. I've seen this in a couple, maybe even 2 or 3 different books. And they've always written the greatest integer function like this. Okay, I've never seen the int. Doesn't mean that books don't use it or he's wrong or anything. Doesn't mean that at all.
So, it must be 5x in there.
Well, watch this. If I put, oh, how would they do that? They'd probably put 5. Okay, this is probably, they probably would do this. 5 times greatest integer function of 1.25. So this thing in the brackets means the greatest integer function, right? And what does that mean? He did explain it, but he just kind of verbally explained it. I thought it would have been a better idea to show it on a number line. And then let's do, and he did explain it, okay? So I'm not saying he didn't, but I just think to see it would be a difference. Now, if I said the greatest integer function, he gave a definition of it, and it's supposed to something like the greatest integer function is the whole number that's less, it's the greatest integer less than the number that they give us, okay? So if they give us 1.25, 1.25 would be right here, okay? What's the largest integer? You know what an integer is? It's no decimals, no fractions, okay? We could say whole numbers, but a negative number is not a whole number, is it? So we can't just say whole numbers, so we say integers. So it's the largest integer that is less than 1.25. So this is 1.25 right here. What's the largest integer that's less than 1.25?
Would it be 1?
It'd be 1, right? Because, I mean, 0 is less, isn't it? Negative 1 is less, negative 2, negative 3, all those numbers are less than 1.25. But what's the largest of all those numbers that's less than 1.25? 1 is. And that's all it is. It's that simple, okay? So if I was to do this, what would I do? It's 5 times, right? Because if this is out front of this, 5 times what? What's the greatest integer of 1.25?
Would it be 5?
No. Just this. What's just this right here? Forget this 5.
1.
Right. What's the greatest integer function of 1.25? It's just a 1, isn't it? Okay. So this is 5 times 1, which is 5. Does it make sense? That's it. That's all it is. It's real simple. Okay.
I got that wrong.
Now, this is where it gets a little tricky. What if they said the greatest integer function of negative 2.7?
So it would be negative.
Where is negative 2.7? Negative 2.7 is here, isn't it?
So it would be negative 1.
No.
Negative 2.
That's why I did the number line, because it's hard when you go negative. It's kind of hard. What's the largest integer that is less than negative 2.7? Well, here's negative 2.7 right here.
Less.
It's got to be less than. You always have to go to the left.
So it's going to be negative.
It's negative 3, exactly. You see that? You always have to look to the left. And sometimes when we go negative, we're not thinking 3 is to the left, are we? Okay, we always think 3 is to the right. But when you talk negatives, though, it's in the other direction. Make sense? So that's where it gets a little tricky. That's where I thought it would have been really nice for him to put a number line and to explain that. Okay? So what would be the greatest integer function of 0.2?
Would it be 0?
It'd be 0, exactly. 0.2 would be here. What's to the left of 0.2? It would be 0. What's the greatest integer function of negative 1.3?
Negative 2.
Yep. Negative 1.3 would be about right here, wouldn't it? And what's the largest integer that's less than negative 1.3? It'd be negative 2. You got it? That's what it means. That's what the greatest integer function is. Make sense a little bit?
Yes.
Okay. I knew you'd have a little bit of a question on that, so I wanted to make sure we did that. So let's look at number. This is, what lesson is this? Is this still 35 or 30? This is 36 now, right?
Yes.
Okay. So problem set 36, number 21. All right. It's got a big whole long word problem. I'm not going to write the whole word problem out, but it says telephone company charges $1.50 for the first minute of the call, 45 cents each additional minute. The cost of international can be represented by this function. So they actually tell you the function. You don't have to make it up yourself. All right, so let's write it down. So it's 0.45. Then they put INT. I guess we'll just do it the way they do it so you're familiar with it if you see it again. Remember, that's that greatest integer function of t minus 1 plus $1.50. It says where int is the greatest integer less than or equal to t. It says use this function to determine the cost of an 11 point, so watch. So the it's an 11.25 minute phone call. So that's T, isn't it? That's the time, how long you're on the phone. 11.25 minutes, 11.25 minutes. And that's basically that whole word problem just summed up in that information right there. And they ask you to find, use this function, to the cost. And so that's what the C is. That's the cost of the phone call. Does that make sense? Okay. So what are you going to do? You're just going to put it in here. So it's 11.25 minus 1, but you're taking the greatest integer function of that. Do what's in the parentheses first. So what's 11.25 minus 1? It's 10.25, right? And you're taking the greatest integer function of 10.25. What is the greatest integer function of 10.25? What is, it's 10, right? Because if you go to the left of 10.25, remember this is positive. If you go to the left, the largest integer is going to be 10, isn't it? All right. So really, all this boils down to is this: C equals 0.45 times. Again, what did all this come out to be? It just came out to be a 10, didn't it? Right. And then plus 1.50, and then just do it. Yeah. This is what, 4.5. Do this without a calculator, can't you? And that's 1.5, and that's what? 6. So $6 to make that call. Yep.
That greatest integer thing was a little bit confusing. Now it's really
good.
Really easy.
Yeah. It looked real weird before, but now that you understand what's going on, that number line, visualize that number line, okay? And if you can't visualize the number line, actually put a number line there and say, okay, I've got 10 here and I've got 11 here. Where's 10.25? It's right there. So what's the greatest integer function of this right here? It's just to the left. Go to the next whole number or next integer. I shouldn't say whole number because they could be negatives. All right, go to the next integer to the left of that number we're trying to find. We good?
Yes.
All right.
Any questions?
You sure? Oh, chapter 6 is trigonometry.
Yeah.
That's my favorite. I love trig. Do you like it? No, you don't like it? Oh my goodness. I thought everybody liked it.
I like it in geometry, but like my sister's doing it in pre-calculus, and it's a lot more. Like, what I did in geometry was just like,
it's baby stuff.
Like,
exactly. You're exactly right. It's just a foundation in geometry. Trigonometric. That's a cool word too. It kind of rolls off the tongue, doesn't it? Trigonometric. All right, enough of that. Are we finished then? Everybody good?
Yes.
All right.